Hey everyone, I'm Brandan. I work on Polygon Zero alongside Polygon Hermes, Polygon Maiden, and Polygon Nightfall. And so I guess my talk is going to be about some of the challenges right now and then challenges in the future of building really scalable L2s that are powered by zero-knowledge proofs. I guess some background. So we joined Polygon late last year, and so we're, I guess, fairly recent to the L2 space, and it's great to be here and be among so many great teams. So I guess as an outline, we're going to look at some of the challenges for zero-knowledge L2s today, our approach to solving them, and then some of the future challenges that we anticipate seeing. So I think over the last few years, it's safe to say that there have been some pretty bold promises for throughput on ZK rollups. So we've seen 2,000 TPS, 3,000 TPS, 20,000 TPS. And I think if we look at the current state of what deployed zero-knowledge solutions can do right now, there's a gap between what we can do in theory and what we can do in practice. And so how do we explain this gap between the theoretical and what's currently possible? I think it's fairly easy. The problem is that generating zero-knowledge proofs is really slow. And so we're going to look at three options to sort of overcome this challenge. So the first is like one thing that we hear a lot is generating proofs is massively parallelizable. It doesn't matter how fast proof generation times are. We can just generate them in parallel. And so the idea here is that we can take a block of transactions, we can arrange them in a binary tree, and we can use recursion to aggregate all these proofs, which are generated in parallel, into a single proof, which verifies a block of transactions. So what's sort of left unsaid, I think, with this answer is that if proof generation times are slow, especially at the transaction proof level, that's still introducing a lot of latency, and it is really increasing the hardware requirements and the amount of machines that we need to run our rollup. And so this is sort of an unsatisfying solution, and I think like we can see with existing rollups that generally suffer from low throughput and high latency, that this is not necessarily a satisfactory answer to our problem. So the second approach is we can use fancy hardware. So it doesn't matter that we have slow primitives. We can build implementations that run on GPUs or FPGAs that will necessarily be faster. The problem is that if we're stuck with slow primitives, especially primitives that use elliptic curve cryptography and operate on 256-bit fields, first of all, the implementations are fairly difficult on GPUs and FPGAs, and the speedups are fairly modest. So up until this point, in general, speedups moving from CPUs to GPUs have been about 4 to 5x. In the future, this might increase, but this isn't sort of a cure-all for increasing performance. And so the third option is the one that we've taken at Polygon Zero and in Polygon in general, and that's to build faster primitives. I'll let Hilo take his picture. And so to sort of give some background, we can think of a snark as combining two components. So there's an information theoretic argument and then a polynomial commitment scheme. So we can think of Planck, which basically gives us a way to arithmetize circuits and a way to check a relation between polynomials to verify that a particular assignment to gates in arithmetic or wires in an arithmetic circuit is valid. And the way that we check or we evaluate polynomials is with a polynomial commitment scheme. And so, for instance, most projects use KZG, which relies on pairings to basically commit to and then prove openings of a polynomial. And so the polynomial commitment scheme dictates the size of our finite field. And so in general, when we use Starks, which rely on Fry, most implementations like Starkwares uses 256-bit primes. And then when we use elliptic curves, again, we're sort of limited or bounded below by in the size of our field. And so at Polygon Zero, we built a new proving system called Plonky 2. And we can think of it as an approach to building vastly more performant snarks and starks. And basically, we can think of the advance as having two parts. The first is moving from big fields that have a minimum size of 256 bits to small fields, and then adding recursion to Fry, the polynomial commitment scheme used in Starks. So, oh my gosh. The goal is, so the field that we use in Plonky 2 and in Starky is called the Goldilocks field. And it has a really interesting structure. And it was, I guess, discovered by, well, I won't dox him, I guess, but by Hamish sitting over there. And so I guess there are a lot of really interesting properties of this prime, but I guess the first is that it fits in 64 bits. And so obviously on modern CPUs, they have a native 64-bit word. And so it's much more efficient to be able to express field elements efficiently in modern CPUs. And the second is that the algebraic structure, the number theoretic structure of this prime allows us to really efficiently do arithmetic on CPUs. So I guess the second aspect of Plonky 2 and the speedup that we've seen is there's this trade-off that's inherent in Fry, where we can choose between either having fast provers, so proofs, we're able to generate proofs very quickly, but they're very big, or we can have slow provers that have smaller proofs. And so without recursion, we have to sort of pick a point on this spectrum where the proofs are big, like fast enough that we can reasonably generate them, but are still small enough that they can be verified on a system like Ethereum. And so this sort of constrains the way that we use Fry if we don't have recursion. Like I think for Starkware, they have to prove a large batch of transactions, and so there's sort of a requirement that they pick a rate or a blow-up factor that results in proofs that are small enough to have low gas cost for verification on Ethereum, but are still fast enough to be generated in a reasonable amount of time. And so with Plonky 2, we showed that it was possible to do recursive Fry very efficiently. And so this allows us to basically take advantage of both ends of this trade-off. So for very compute-intensive tasks, like generating a proof that an Ethereum transaction is valid, we can use a configuration that maximizes prover speed, even at the expense of huge proofs, because those proofs will never actually be posted to Ethereum. So what we can do is, like what we do in Polygon Zero, is we have a batch of transactions. We prove that each transaction is valid in parallel using our fast proof speed configuration. It doesn't matter that the proof sizes are large, because we recursively aggregate all of those proofs into a single proof that has a small circuit, and then we can wrap that once more in a very size-efficient proof, so we can take advantage of low gas costs. And in the future, we're working on wrapping that once more in a pairing-based proof to fully minimize verification costs. So an interesting thing about Plonky 2 and Starky is, so Plonky 2 is a proving system that's based on Plonk, and Starky is a proving system that's based on Air. And so these two arithmetizations have different properties, and they're good for different things. So in Plonk, if you think about how the arithmetic circuit works, gates can be routed arbitrarily to other gates, or I guess wires can be sort of routed to, I guess gates can be routed to arbitrary gates, whereas in Air, each gate is only has access to the immediately preceding and following gates. And so Air is really good for something like a VM, where you have a computation that is sequential. And Plonk is really good for building arithmetic circuits that are specially tuned for a particular use case. So, for instance, we have an ECDSA circuit that's built in Plonky 2 to maximize efficiency of verifying ECDSA signatures. But our System 0 VM is written in Air because it's a model that makes more sense for a VM architecture. So the result of all of this, of Plonky 2 and Starky, is that we have lightning-fast zero-knowledge proofs. They're fully transparent, so we use Fry, which is obviously a fully transparent polynomial commitment scheme. And they're way more performant than existing primitives. So the benchmark that we've made public is it takes 170 milliseconds to generate a recursive proof on a MacBook Pro sort of readily available laptop. And we anticipate that this will decrease somewhat substantially. And this is 100 times faster than the recursion using BN254 with Plonk and KZG. And so a benefit of this approach is that there are no cycles of curves. There are no accumulators like in Halo or other recursive schemes, and there's no deferred computation. Each Plonky 2 proof can recursively verify fully a child proof, so we don't have to worry about some computation that's deferred to the verifier. Obviously, the drawback for using Fry is that proof sizes tend to be quite a bit bigger than pairing-based proofs, but this isn't so bad. So Plonky 2 proofs are about 45 kilobytes, and as I said, we're working on further compression with pairing-based proofs. And so the result is for Polygon Zero and for Polygon Hermes and Polygon Maiden, we can take advantage of really fast recursion and really fast proof systems for transaction proofs. So we can have faster proof generation times for transactions, which tend to be more expensive, and we can efficiently aggregate all these transactions into a single proof that we can post to Ethereum. So one sort of interesting thing is that even if we have fully maximally efficient ZK proofs, I think that there's something that's maybe not discussed as much, which is that there's still like a further limitation for ZK L2s. And so if we ask the question, how do we increase L2 throughput by 1000x, we still run into this issue where proof generation is very easily parallelizable. So we can simply add more compute to process more transactions and generate proofs in parallel. And so we have sort of a sublinear slowdown for proof generation. But we can't do this with sequencing. So if you think about how an Ethereum block is processed, transactions can contend for the same state. So if we have in a block of transactions some trade in the Uniswap pool, we might have later on in that block a trade in the same pool. And so we can't simply distribute all of those transactions to separate provers or to separate verifiers and expect to get a valid result, because each transaction can touch the same state. And so because sequencing is not parallelizable, this ends up being a pretty significant bottleneck if we have fast zero-knowledge proofs. And so we'll look at three options to address this. The first is we could simply have, if we want to increase throughput by 1000x, we could simply have 1000 rollups. But the problem here is that what we really want is to increase throughput while maintaining composability. And so if we have 1000 rollups, we'll have this issue where we need to move state and value and assets between rollups. And so, and that's both sort of difficult for users to reason about, and it also creates a lot of communication overhead on the main chain. So one option that's been proposed is by Starkware is to do an L3. So we could have our L2, and then we could sort of have rollups on top of rollups. So for let's say a Uniswap pool, or for some specialized application, we could create a rollup that's specially tuned to verify transactions for that application. And so if you wanted to trade in a pool, you could deposit assets from the L2 to the L3, and then that L3 would be sequenced, and proofs would be generated by a specific validator, or set of validators. And so this is nice because we're no longer limited by the sequencing bottleneck on L2, and we can design rollups that are even more efficient for proof generation for specific cases. The problem here is that we can't, it still sort of limits composability on our L2, because we can't sort of atomically take state and assets and transact in an L3. Like it would be difficult to take out a flash loan and use it to trade in a specific Uniswap pool on an L3. So it gets rid of the overhead of inter-rollup communication, but there's still some issues with composability. So this is sort of a half-baked idea that we can end on. Another option is what we could call like auto-parallelized sequencing, which is we could have sequencers, when a transaction is submitted to the mempool on our L2, sort of make a list of all of the state that that transaction relies on. And then given that list, we could separate or shard validation of that transaction to a specific set of validators. And so we could basically parallelize sequencing. The validators in charge of a particular shard could generate proofs and verify that a particular set of transactions are valid without imposing that burden on the entire validator set for our L2. And so I think I'll end it there. I guess to sum up, there are some serious scalability challenges for ZK rollups right now. We think that by using better primitives, we can overcome them. But eventually, we will be bottlenecked by sequencing. And I think that that's something to sort of address and to think about strategies for overcoming if we want to increase the user base of Ethereum by 1000x. So thanks, everyone.
Well, thank you very much. We still have some time for some questions. So while waiting for the brave person. I will ask a question then. Given the complexity of this construction, does it even make sense to talk about snarks and starks anymore? This is so blended that now we need to find out a new name for all this.
Yeah, I think that's a really good point. I think the line for years, I think that there was an easily definable gap between snarks and starks, but now that we're sort of mixing arithmetizations and polynomial commitment schemes, I think, yeah, we're no longer living in a snark versus stark world. We're living in a Plonky 2 world. So,
what about the trusted setup?
So there's no trusted setup on Plonky 2.
All right, so then stark, right?
Well, so
snark component.
Yeah, so there's like a lot of people, I guess, just to be pedantic, the S in Stark actually it doesn't stand for succinct, it stands for scalable, and so that refers. What?
First T, right? Transparent, no trusted setup. Stark.
Yeah, but the S, refers to the repeated structure in a Stark, and so I think, but for all intents and purposes, I think there's very little difference.
Any more questions? All right, first one here. I think the box is somewhere. No, yeah, first box over here.
Can you elaborate on the security parameters that were being used when you compared BN254?
Yeah, so I'm not sure because I'm not sure what the security level is for BN254 because I think for pairing-based curves you want like a much bigger base field size. But so we're targeting 100 bits of security for Plonky 2. So yeah, I think because I know that I'm not sure if BN curves are vulnerable to that attack, but I know for BLS there's like some hypothesized minimum field size of like 380 or 440 bits. So, but yeah, for Plonky 2 it's 100 bits. Yeah.
Okay, we've got one more.
Hello?
Hey.
So you mentioned low-level primitives like vector instructions and operating over a nice field. Mm-hmm. And all of that combines into a recursive circuit that's 2 to the 12 gates and sub-second proof generation. How does GPU acceleration fit into that model?
So I am not as qualified to talk about GPU and FPGA implementations as people sitting over there, but so my understanding is that because the field size is so small that it will be much easier to build GPU and FPGA implementations for Plonky 2, and further that those implementations will tend to be more efficient than like equivalent ECC proving systems. And so I think that's definitely in our roadmap is to build GPU and FPGA implementations. But we feel like the performance is at a really acceptable level for CPUs, and so it's not like an immediate priority for us.
Any more questions? Yep, we've got one here on the back.
Sorry, where?
Thanks. So, hello, my question is, what is the throughput currently, I mean, number of transactions per second at this moment, what you have, and what do you expect with all this wizardry that you're doing in some future? What's the realistic number, let's say, in some realistic time from now? Yeah,
so we're still in active development on our EVM-compatible VM, and so I don't want to get myself in trouble by making the same inflated TPS claims that I referenced in my slide. And so I think, our target is sort of like Solana level or greater throughput, but obviously with a higher degree of decentralization and verifiability. And so that's our target, and we think, like, based on our progress so far and sort of some napkin math that we can achieve that, but we're still in development.
All right. Thank you very much again, Brandan. It was a fantastic presentation.